Polar orbit means the satellite will pass through the pole, North Pole South. That we call the polar orbit. Another is a low Earth orbit. Low Earth means very close to the Earth, maybe 700 kilometers from the ground. And geostationary is very far. So based on these three locations, we have three different chambers. That chamber can simulate this environment in our lab. The first one is the geo chamber. This is our geo chamber. And we can create the high energy electron, and we bombard the electron on the solar coupon or electronics. So we can check the electronics performance in the geostationary orbit. So we call it a geo chamber. Okay. And that is, you can see here is a one high voltage source, 20 kilovolt DC. Okay. And most of our experiment is run on 10 kilovolt DC. This is a polar orbit chamber. Okay. You can see here electron gun. Here is some high voltage source, some current probe. Probably you know current probe, right? You know voltage probe that measure the voltage, and current probe that measure the current passing through the wire. And here is a 16 channel oscilloscope. I saw some oscilloscope in your lab. And how many channels?
2 channels.
2 channels. Here is a 16 channel. So 16 different location data we can collect in a twinkling of eye and very high speed. And this is Leo chamber, low Earth orbit chamber. We have here ECR plasma source. I don't like to explain what is ECR. It will take a long time. Anyway, we have some turbomolecular pump to make the vacuum. And we have here, feed it through, we can pass the liquid nitrogen. Have you been seen any liquid nitrogen before?
Okay, no, in movies.
In movies?
In movie.
Okay. In moving means?
W2.
Oh, okay. So liquid nitrogen actually is look like actually Sprite. Colorless, but always bubbly. For a short time you can dip your hand. I did it. For a short time only. So just this is okay. But long time no. It look like a Sprite actually. Always bubbly. If you keep it here within short time it will be vaporized. Okay. Colorless liquid. So we can pass liquid nitrogen through this. This is vacuum chamber. So liquid nitrogen always pass through some tube and makes the system cool. And this is our actually the first satellite. We name it ROBU, and this is the flight model FM. Flight model means this satellite is just before launching. And this is a 30 centimeter cubic satellite, 30 centimeter, and 7 kilogram. 7 kilogram, you know how much it is. So very small actually. So we call it nano satellite. And this satellite revolving around the Earth from 780 kilometers from the surface. 780 kilometers, and it's a polar. So it's passing through North Pole, South Pole. And its orbit time, can you imagine how long it is? Orbit time is one rotation time period. 98 minutes. So within 98 minutes it rotates, it revolves around the Earth.
How many kilo in 1 hour?
So you can calculate. 800 kilometer radius of the Earth plus 800 kilometer, and then you can calculate. Anyway, so that is our first satellite. And I have some other talks on this satellite.
Why there are so many cables?
Because we are testing the satellite. We attach here many thermocouples. You know thermocouple to measure the temperature. Okay, and here it will be in hot heat cycle and cold cycle. On hot cycle and cold cycle, we run the satellite, power switch on, and we check either it's running or not. That is our objective. And we have here ECR plasma source.
So we have the extended panel or
no, simple this type of wire that will act as a VHF antenna to emit to track communicate. This is only for communication.
For power.
No, for power it will run by battery. And we have solar cell, very small solar cell, and it can generate the 300 volt. 300 volt, and this is so far the highest voltage we could achieve in space. We applied for what is that? We applied for Guinness record. Yet we have received any answer. Anyway, this is very interesting. And this is another chamber. We name it square chamber. Most of the chambers are in the cylindrical shape, but this is in square in shape. And then here we have a plasma source, and this is the argon gun, and here is a cryogenic pump. Probably you know what is cryogenic pump. This pump produces the very low temperature, and very low temperature gas are absorbed on the body. Right? Very simple. This way we could achieve very high vacuum. So that is actually our cryogenic pump. This is plasma controller. And this is our atomic oxygen chamber. Atomic oxygen means actually oxygen gas is passing through this chamber, and from here we have carbon dioxide laser gun, and that laser hit the molecular oxygen and it breaks down. And we keep our device or different sensors or different film to study the atomic oxygen degradation effect. Okay. And this is our ELF chamber. ELF means electron emitting film. We designed the ELF in this chamber, so we name it ELF chamber, and we measure the surface potential. We hit the sensor by electron, and surface potential changed, and then we can scan. And that is a non-contact method. That means there is some distance between the probe and the surface, so that that probe cannot affect anything. Okay. And electron emitting film, actually how it works, very simple. I think I better skip it. I better skip it. This is very big. And this is our satellite. Okay. On this satellite, this is the two sensors I designed. One is ELF and another is SCM, and we have the related circuit to measure the potential and the emission from this one. And this is our ROBU, and it passes through North Pole, South Pole. And you know, on the North Pole and South Pole, the field is very intensive, flux is very high. So ion density is very high here. So the Canadian people can see the bright sky at midnight and different colors, right? Anyway, so when this satellite passes through this system, there will be some charging and discharging. And in that situation, this will start working. And we receive the data. This is the circuit. And when this is actually the South Pole. And you can see this is actually the South America. And this is the South Pole, and the satellite passes through this line. And when it passes here, we switch on the signal and we get some data from this ELF and SC. This is the satellite data. That means our sensor is perfectly working on the satellite. So that is our very good achievement actually. And this is another chamber we call the UV chamber. We put some sample here and pass the UV lights to check the degradation effect. And this is another UV chamber, and this is some physical test of some material. And this is secondary electron emission chamber, and this is very high speed oscilloscope. This is 1, 2, 3, 4, and we called it Lecroy company. And this is itself a computer actually, and touch panel, everything is touch. Okay, very high speed. I can skip it. So we have another center we call the nano satellite testing center. Different types of nano satellite can be tested here. Okay. And this is started on July 2010. The objective is to test nano satellite up to 50 centimeter cubic and 50 kg. This is our maximum limit. And below this range, we can test any satellite. What we test? Thermal shock, outgassing, thermo-optical properties, vibration test, antenna pattern test, thermal vacuum test, thermal cycle test, EMC test. Probably you know EMC. electromagnetic compatibility. When you use any iPhone or any cell phone, so there is a radiation, right? And how much is the intensity of the radiation? Is it harmful for the body or not? So before selling to the market, every electronic equipment should be checked. That check is called EMC. This is compulsory for all electronics. Okay, then it's come to the market. Then we can use it because they confirm that there is no severe effect. Anyway, we can do that EMC test. And you get some leaflet, right? So you can see many pictures over here. And so far we tested many satellites. One is the Kagoshima University satellite, Venus probe satellite, KIT satellite ROBU, Kyushu University satellite, Kanagawa University satellite. That satellite has been tested in our center. And this is the vibration test machine. So we put the satellite here and we start vibration. Because when it launched by rocket and satellite is different things, you know, completely different. Okay, so when any satellite is launched by a rocket, every rocket has its own vibration mode. And we vibrate this machine to the same mode to check this satellite is completely adaptable with the system or not. So we use that vibration machine. This is actually thermal cycle and heat balance test. This is a very big vacuum chamber. We can test this sort of system actually. And this is the our KIT satellite for you too. This is a revolving. And you can see there is some bending steel part, bending. And when it will be on circuit, it will start straight. That means that will be our antenna. And through this antenna, it will communicate to us. And what is the objective of ROBU? ROBU objective is to teach the student how to make satellite, first objective. Second objective, so there is a different stage. Okay. Second objective is day by day we need more powerful satellite. But you know ISS, International Space Station, that satellite is running by 160 volt DC. But in future, there are many satellites coming. They will need more power, more high voltage. This is why we selected 300 volts and we succeeded. Okay. So this is the solar cell actually, very small solar cell that ultimately help to make the 300 volt. And we have some other our research findings. We have many results, but that result should be confirmed in space. Otherwise, we cannot show this is applicable. So this is why we use some film over the solar panel to stop the electrostatic effect. And unfortunately, we still haven't any data. That means still it's working actually. If we get the data, that means there is some issue. And we have one camera. That camera is designed by University of Surrey, UK. We have a collaboration with the University of Surrey. And that is the picture taken by our ROBU satellite. This is a real-time picture. And actually, this is the Kyushu island. And this is the other island. This is Japan. And this is Korea. And in USA, there is a big electronic company named Trek. They produce many electronics. And we have some collaboration with that company. We tested their product in our lab. And they selected this equipment to launch by the rocket, by the satellite. And it was launched and it worked perfectly. So they are very happy actually. So their market value is now very high because they can say our product is very sustainable in space. This is our electromagnetic field. I already told you. And you don't print this one. This is the other picture taken by. This is the one typhoon. Typhoon means actually this is a storm actually. Cyclone. Okay. That was captured by our satellite. And our next project, ROBU 4. This is the much bigger, and it will be around, I guess, very close to the 50 kg. It's a big satellite, and it's a commercial satellite. Commercial satellite means actually different parts are collected from the commercial company. They give us money to make the satellite, and we will test it, every device. And if we successful, then they can sell their product to other satellite company. So this is a commercial satellite, and we have here two cameras. This side one camera, another side another camera.
What the name is ROBU 4? Why is ROBU 1?
ROBU 3, we applied for the ROBU 3 budget, but unfortunately we did not succeed. It depends on budget, and we have many plans actually. So ROBU 3 budget was not successful, but ROBU 4 budget was successful. So we are going to make this ROBU 4. And Mr. Jahangir, he is here. He will work on this camera, the image processing. He has already been selected for the scholarship. And this is another side, two cameras which we work. And we also work ISO. There are many ISO systems. ISO means there will be one standard system. Everybody should follow that system. So ISO 11221, this is actually ESD experimental system. What we need for ESD test? What the chamber size, what the coupon size, what will be the voltage, what will be the current, everything is defined. And you have to, if you say that our solar panel is ESD proof, you made a solar panel, okay. So you are going to sell it. Then you have to say our product is confirmed by the ISO system. Then you can sell your product. That ISO is designed in our lab. We the European Union and the NASA, USA, the three bodies work together to define the ISO. And we have some other plans. So spacecraft charging potential estimation. This is ongoing project. And another is a nano satellite testing system. We have system, but we are not certified. So we have to make the definition for the standard. So we have been working on that. And also we have the United Nations Japan long-term fellowship program. We call it postgraduate study on nano satellite technology. Okay. And this is offered by the KIT, and it is collaborative with the United Nations Office for Outer Space Affairs. So we are collaborating to each other. And there are some mission, please keep it actually. And this scholarship is financed by the Japanese government. And the starting date is October each year. So you have to, if you want to apply, you have to apply earlier. This is the starting date. And this year, 28 countries, students from 28 countries, total 83 candidates applied, and 6 have been selected. One from Egypt, Ukraine, Bangladesh, Romania, Singapore, and Sudan. This is actually this year, Mr. Jahangir, for next 4 years, 3 years. And if you want to check, please visit the website. There is a more detailed information. And what we can do with our satellite. Probably you know more of this, but this is for we can work on the telecommunication if we have our own satellite. We can save our money because you know there are many mobile companies. Okay, they actually buy the downlink, uplink from the different companies from our side. So when you talk, we have to pay the money, and that money goes ultimately to the satellite company, right? So we can work on this field through this system. We can work on GPS, military purpose, and some weather forecasting and pattern analysis. We can do many things with the satellite. And the flood analysis, surface mapping on agriculture. There are many fields, so we can work on that. So that's all. That's all. So if you have any questions, I will
So
answer.
we have a silly question that is like normally the traditional satellites we see they're like being like in the solar panel. it has a different structure. Why
Yes.
is that?
The different structure depends on the power you need.
Okay. The larger
If you need more power, you need more bigger power generation unit. Simple. And many satellites are running with 5 volt, only 5 volt.
the,
So it depends on the demand actually, what you want to do with your satellite. And how many power you
the
need.
panel we saw here, the solar panel in that satellite, it's sufficient.
Sufficient. Good enough. Good enough. That is our new invention actually. So we don't need very big satellite. Big satellite means actually you need very big facilities. Very big chamber. And very big chamber means you need at least 3 days to evacuate the system. You need power, you need machines. So satellite big means everything is big. Okay. So nowadays your demand, your objective is very concise. Very 1 or 2 project is good enough. So this is why nowadays small satellite is very popular. Yes.
You mentioned we use battery. So
Yes.
according to my understanding, battery will go down after.
No, is it rechargeable?
Rechargeable, but it will go down after 1 year or 3 years.
Yeah, our project life is 1 year. 1 year already gone, but still the satellite is running. So every satellite there is a project life. How long it will be working?
So your project life for 1 year.
Was 1 year. Still it's running. So this is our benefit.
So why can software engineers contribute?
Very good. Because nowadays every electronics is run by the peak. Peak means you have to design some program. I saw one data actually. So 8 minutes. The F data. What do we? 8 minutes. What is the data? Of this data. This time resolution was 1 second. That means every 1 second it is getting one data. How do you define one analog circuit can control by 1 second? Without peak it is not possible. And there is a program. You need a program.
The image processing part that the research is going to work on.
Image processing means actually he is very expert on that. So far, anyway, image processing means after taking the camera picture, that signal is converted to the electric signal, and that electric signal is converted to the microwave, and that microwave is coming to the earth, and then you analyze the data. So there is a huge work on that. Yes, anymore.
So near the beginning of the lecture, you said that the maximum amount of damage is being done by the solar panel.
That's right.
So after launching the satellite, how do you access the damage report?
Very good, very good. So far, no device is detected. No device is invented to specifically locate the discharge location. But we think that if there is no power generated by the satellite, no signal is coming from the satellite, that means there is some wrong. And some people, there are some data actually. Based on this data, this graph was done. What is that? This may be over here. This is actually based on money. Okay, then they analyze actually. They convert this electronic equipment, convert to the money, and they analyze how many money is damaged due to the solar panel.
So how do you determine that the damage is actually the solar panel, not in the circuit? Or
Getting the data actually. If there is no power is generated, that means something is wrong on the solar panel. That is the only way. This is why in ROBU 4 we are making one onboard digitizer actually. It's a one kind of oscilloscope. So far there is no satellite which carry oscilloscope itself. So ROBU 4 we are going to make one small oscilloscope and we will build it on the satellite, and we will collect the current data, voltage data, and some camera to take the picture. And this is very simple. When there is a discharge, there is a sudden pass of current, right? And when some current is passing, there is a level. If this current is passing through this value, then it will trigger your camera. Desynchronize. So then you can detect. Yes, there is a specific location.
So is it according to your making cost or
Making cost is based on money. Based on money.
Sir, I've seen some physics in this while working with some game engines where we can make a virtual character into a world-like place and put it through some kind of obstacles that we actually face, like gravity. We can set gravity, we can create storm, we can make other some vector calculations. Do you use some sort of software before sending the?
Very nice question. Yes, we have one software. Probably you know NASCAP 2K. Have you heard this name? This software is made by NASA. They are very familiar with this NASCAP 2K. And in East European Union, they make SPIS, S-P-I-S. Their software is designed by the European Union, and they use some raw data, and then they analyze the satellite characteristics in the storm. Satellite characteristics under thermal condition, at high temperature, at low temperature. There are some many simulation software, but they are lacking of raw input data. So our basic research is based on that input data. We need many input data. Otherwise, we cannot run the software. And in our lab we have a MASCAP, Multi-Utility Spacecraft Charging Analysis Tool. This is software. But you know, in software you need some input data, right? Then it will give you the final data. So we have that software. That is completely designed in KIT. My professor, Professor Cho, is very good in simulation. He graduated from MIT and returned back Japan to start this business. Yes, please.
How a student can be involved with your research, or how can
The best way, if we can start any collaboration. We are ready to start the collaboration. KIT is ready. Okay. If we have some good negotiation with the Brack University, then some student, bachelor student, they can go for 3 months or 6 months. Because in Bachelor 4, probably you have to write down some thesis, right? You can work there. And then you can submit your report anywhere in the world. We can check it online. So you have the experiment system. You have the high quality facilities. You can use that system. If we can success on collaboration. And personally, I like to start this type of work in Bangladesh. This is my personal opinion. Yes, please.
Sir, you talked about some orbits,
Yeah.
and one orbit was like polar orbit.
Yes.
Does the satellite circles the polar axis, keeping the polar axis in center? Like
It depends actually. Satellite actually is moving, but all the time it is not fixed. There is some deviation each time. Okay, so who are interested on orbit, please visit Dr. Colin's lab. I installed one software and I showed our satellite audio 2 that is revolving. So Mac is unable to run the software. So please visit this room, then you can get some clear picture how it's revolving.
Does
Yes.
ROBU has capabilities to correct this deviation, because maximum satellites have propulsion system, but does nano satellites have those propulsion systems to?
Now, the propulsion system actually is a different case. Propulsion system means actually one satellite is revolving through this one orbit, but after 10 years or after maybe 1 year, you think that okay, we have good enough data on this orbit, we need to shift the orbit. In that case, we have to beforehand install the propulsion system, maybe some plasma or something like that, so that it moves, it deviates from the system. But it needs a very precise experiment, which is very expensive, costly. But there is many satellites, they can change their orbits, possible. So, but we don't have that system.
Within the nano satellites, you can those?
Possible. And there is another term, reaction wheel. Reaction wheel means they will start rotate one fan. You know, when a fan is rotated, their movement will be shifted because it's a floating. And somebody push here, your deviation will be changed, your rotation will be changed. So it will move another